Welcome to the video on antenna field zones. In this video, we are going to see about the regions surrounding an antenna. So once radiations are accomplished using the antenna, we can classify the regions surrounding an antenna into various field zones. So let us see how the regions surrounding an antenna are classified. The region surrounding an antenna can be classified generally into two zones. The first is called as the near field region or the Fresnel zone, and the second one is called as the far field region or the Fraunhofer zone. So based on the amount of radiation and the distance, we classify the regions surrounding an antenna into near field region called as Fresnel zone and the far field region called as the Fraunhofer zone. Now this diagram depicts the various regions surrounding an antenna. At the center, we consider this to be the antenna that is present. Since the fields are imaginary in nature, we construct an imaginary sphere around the antenna. Since the field components or the regions, the fields they follow the spherical coordinate system, we construct the field or the region surrounding an antenna in the form of a sphere. And with respect to the boundaries of the sphere, we are going to define the various regions surrounding the antenna. So the first region that we classified is called as the near field region. The near field region, as we said earlier, is also called as the Fresnel region. The near field region is categorized by if the radius is 2L square by lambda. So the radius of the sphere that we have constructed, if it is less than 2L square by lambda, where L is the maximum dimension of this antenna, either the length or the width, the maximum dimension of this antenna is what we called as L. And lambda represents the wavelength. Wavelength is nothing but C by F, where C is the speed of light and F is the frequency at which the waves are traveling. So, any region within this particular boundary where the radius is 2L square by lambda, we call this to be the near field region or the Fresnel region. And any region outside the sphere where the R value crosses 2L square by lambda, we call it to be the far field or the Fraunhofer region. Only in the far field or the Fraunhofer region, the actual radiation of the antenna starts. Till the near field region, we cannot observe the radiations properly. The shape of radiation is somewhat random, but only after the radiation crosses this boundary between the near field and the far field region, we can observe the radiations of an antenna as required. That is why we classify the antenna regions as near field regions and far field regions. So any field within the boundary of 2L square by lambda, where L is the maximum dimension of the antenna and lambda is the wavelength. Any distance within 2L square by lambda, we call it to be the near field or the Fresnel region. And if the distance crosses 2L square by lambda, that is called to be the far field or the Fraunhofer region. Next, let us go to a still in-depth classification of the regions surrounding an antenna. The near field can still be divided into two types. One is the reactive near field and the other one is the radiating near field. In the reactive near field region, we cannot observe any radiations. It is a region immediately surrounding the antenna where it is highly reactive in nature. So for example, if the antenna is present and if we try to bring any other component closer to the antenna, then it tries to dissipate the total energy to that particular device. It is highly reactive in nature. That is why we call that region to be reactive near field region. And in this reactive near field region, we cannot observe any radiations from the antenna. The second region, as we saw already, it is called as the radiating near field region or the Fresnel region. Here is where the radiations try to emerge. Actually, electromagnetic radiations, the E field and H field should be perpendicular to each other. Only if the E and H field are perpendicular, the radiations will start from the transmitter and it will travel towards the receiver. But that E and H fields are not perpendicular in this Fresnel region. They try to become perpendicular in this radiating near field or in the Fresnel region. And only after the boundary of the Fresnel region is crossed, we come to the far field region where the E and H fields are perpendicular to each other and we actually attain the proper radiations, proper electromagnetic waves. So as we saw in the previous slide, the boundary between the regions is arbitrarily taken to be at a radius of 2L square by lambda. Sometimes this L is portrayed as D also in certain places, or it is 2D square by lambda, where L is the maximum dimension of the antenna and lambda is the corresponding wavelength. So we can see here, this is the antenna that is present. The region nearest to the antenna, we call it to be reactive region where there are no radiations. So we call this to be non-radiative in nature. And in the Fresnel region, the radiations start to emerge where the E and H fields try to become orthogonal to each other. And once we cross the boundary of the near field, we reach the far field region or the Fraunhofer region where the actual radiations from the antenna start to travel. So this is the classification between the near field region and the far field region. So this is again a similar diagram. So this is the reactive near field region where the radius value is equal to 0.62 root of d cube by lambda. So any value till 0.62 root of d cube by lambda, we call it to be the reactive near field. This is with respect to the point of the antenna. This inverted triangle we consider to be the antenna. So from the antenna till a radius of 0.62 root of d cube by lambda, we consider it to be the reactive near field region. And any region from the antenna till a radius of 2d square by lambda, we call it to be the radiative near field region. And once we cross the radius of 2d square by lambda or 2l square by lambda, we call it to be the far field region where the actual radiations begin. Now let us have a short glimpse of the reactive near field regions and the far field regions. So the reactive near field region is a region which is immediately surrounding the antenna where the antenna is highly reactive in nature. So the reactive component Jx is very much predominant in this reactive near field region. And next is the radiating near field region where the E field and H field try to become orthogonal to each other, and also the field distribution depends on the distance. So since this is close to the antenna vicinity, if we consider this to be the antenna, since this is a little bit close to the antenna, the type of radiation, the shape of the radiation or the nature of radiation depends on the distance that is present from the antenna. And once you cross the near field region, we go to the far field region where the distribution of the fields is independent of the distance. And after this, we acquire the required radiation pattern. So this is actually a proper radiation pattern. And about this, we will be seeing in the next topic. So it must contain a main lobe and we will be having side lobes. The main lobe is one that contains a maximum energy. So this is called to be a proper radiation pattern. And such patterns are observed in the far field region, which is independent of how much far away we are from the antenna. Whereas the radiating near field region, it depends on the distance we are from the antenna. And therefore here too the radiations, the shape of the radiation that we get, it varies and we do not attain the full radiation here. And in the reactive near field region, there is no radiation or very less radiation, and this is the region that is immediately surrounding your antenna space. So hope you're clear about what is near field region and far field region. Thank you.